Hey guys, in this video I'm going to give you a solution to the torque lab and also demonstrate how you can set up the various situations that we used to do the torque calculations that we did. So first I'm going to pull in the instructions for the torque lab to show what we need to do. Okay, so as you recall, the goal is to predict and confirm the forces required to keep a massive beam in rotational equilibrium. So always we're going to predict first and then we are going to confirm that our answer is right. So first, measure the force required when applied 20 centimeters from the fixed point and perpendicular to the beam. So let me show you what that step looks like. Okay, so here's our beam. 20 centimeters is one whole length from the pivot point. Attach our force sensor. And we want it to be in rotational equilibrium, so it shouldn't be moving. And I can read 42 newtons. So I measured 42 newtons at 20 centimeters. So here's the table I want to fill out with all my distances there. I've notated the distances are going to be in centimeters. The predicted forces are going to be in newtons. The measured forces are in newtons over here. I don't have a predicted force for the 20 centimeters because I had no idea, but I measured 42 newtons right there. So what I've actually got here is I've got a measurement of the torque due to gravity. This force, 42 newtons at 20 centimeters, that offset the torque due to gravity. The torque that I pulled with minus the torque due to gravity, that added to be 0, and so the torque that I pulled with was equal to the torque due to gravity. Now, of course, the torque that I pulled with, that's force times distance. Of course, you should have some angular dependence there as well, but I'm going to work as hard as I can to keep this angle to be 90, which makes this whole thing 1. So now since the pulling force should be equal to the torque due to gravity, I can find the torque due to gravity just by taking 42 and multiplying times the 20 centimeters. That's 8.4 newton meters. So when I take all these numbers here, when I take the distance and multiply times whatever my predicted force is, I should get 8.4 newtons meters. And so I can solve for what my predicted forces are going to be. Basically, I'm just doing this. I'm just saying that the force times the distance at each predicted location is going to be 8.4, so I can solve for the predicted force. I get the following values. And if I actually do the measurement, I get the following answers. I get 20.5, 14.2, 10.8, and 8.2. Quite close, and I think I can say that I have confirmed that I understand how torque depends on distance from the pivot point. Okay, so here's the second half of the first part of the torque lab. Pick a point and measure the force required to keep the lever in equilibrium when the force is applied perpendicular to the beam, so the angle is 90 degrees. Pick 4 other angles and predict the force required to keep the lever in rotational equilibrium. Okay, so here's the setup for this part. I've got the protractor right here. I've picked 40 centimeters away because I think that's going to make the measurements easiest. And I've also picked up a technique from somebody in the second class, which was if you put the string on top of the protractor, you can let the protractor just sit there, and then you can measure the angle. Well, first, I can measure this, but of course this is going to be exactly the value that I got in the first part because we were measuring a 90-degree angle. So I'm going to write that down, and I'm going to predict how the force changes as I change the angle. So for my previous data, I know that it took 20.5 newtons at 90 degrees and at 40 centimeters away from the pivot point. So here's the table I'm going to set up. I'm going to pick 4 other angles, which I think are going to be easy and interesting to measure. 90, 75, 50, 40, and 20. And I want to use the same basic idea that I used before. Sum of the torques has to equal 0. In this case, I'm going to change the angle, so I'm going to put the angles in there explicitly. And just like before, I know what the torque due to gravity is because I already balanced it out once. That was right here. That's 8.2 newton meter. So notice that it's not 8.4 like I predicted. That's because I'm using the actual measured value here, not the actual predicted value. I hope that's going to be more accurate. So here's the equation I want to solve. I'm looking for the FP. I'm going to put in all the various angles here. This thing is going to be 0.4 because I know that it's 0.4. And then I just have a number 8.2 here. I'll put those predictions in. All right, and you can see that actually my prediction for the 20-degree one is larger than our force sensors can measure, so I'm going to change that one. So now it's quite a lot larger than the previous one, so we're really going to be able to see the difference, but it's not so large as to break the 50 Newton limit. Okay, so we're back at our setup. All of my values are greater than 20, less than 50, so I'm going to use the yellow sensor. First one I have to check is 75. 75, I get 23. Now I have to check 50. I get 28. Now I have to check 40. I get 32. And now I check 30, and I get 40. Okay, so my results are not quite as accurate as for the distance part, but at least up here, these are quite good, within 1 or even less than 1 newton. Down here, we're around 2 newtons off, but that's within 10%. So I'm pretty happy with this. So now I can say that I understand both the distance dependence of the torque and the angular dependence of the torque. So now it's time to go on to part 2 of the lab, and that is the various activities and specific situations that I presented. So here's the lab description. Predict and confirm the forces on the beam in the following activities. Start by determining the mass of the beam by measuring the force required to keep it in rotational equilibrium. So the key is rotational equilibrium. Yeah, I could just set this on a scale, but that doesn't teach us anything about torque, and that's what we're trying to get to. So here's the setup. My bar. I'm going to attach a force sensor at any location I want. I'm going to use the 60 centimeter location. So I'm applying a force at a 90-degree angle here, and gravity is acting on this bar, which is going to make it go downwards if I don't hold it up. So there's a torque from here and a torque due to gravity as well. So start with our equilibrium condition. Sum of the torques is the torque that I pull with minus the torque due to gravity. So I just put in the definition of torque as a force times the distance from the point of rotation times the angle. And I'm going to do this in the same exact way I did the first part. I'm going to try to keep the beam perfectly level. So if I keep the beam perfectly level, these guys are both going to be 90, and that means that the sine of those angles are both going to be 1. So we really have just the forces and the distances to deal with. So I am going to measure a force at a distance. I am looking for the force of gravity, but I need to know what the distance is from the point of rotation that gravity acts on the bar with. So up to this point in the class, meaning up to until studying rotations, we've always assumed that the entire body acts as a single point. So gravity acts from a single point, and that whole body is just like having a single point. It's got no extension whatsoever. Now we have some extended objects. Our assumption is that the force due to gravity always acts on the center of mass of the object. So it's appropriate to call this an assumption because we haven't proved it, but it actually turns out to be a very good assumption, and you can use some theoretical methods to show that this is actually completely accurate. If it's uniform, it's very easy to show that it acts at the center of mass, but also if it's non-uniform, gravity will still act at the center of the mass, even though you take into account the fact that the mass may be distributed throughout the object. Okay, so here's our bar. The center of mass of this bar, it's a uniform bar, there's no excess mass on any given part of it. So the center of mass, which is marked on the other side of this bar, is right here, right exactly in the center. Take a ruler, divide it in half, that's the center of mass. But what goes in the torque formula, of course, is the position of the force acting on the bar relative to the pivot point, not relative to the end. So the center of mass is here, all the force of gravity is acting here, but the distance you want to put in the torque formula is between the pivot point and the center of mass. So you'd have to pull out your ruler and measure that to get the right value for your particular beam. In the case of the beam that I'm using, the center of mass was 42 centimeters from the point of rotation. I measured before that the force that I pulled up with was 14.2 newtons at 60 centimeters. So by just rearranging this equation to this, I can say that the force due to gravity is the pull force times the distance that the pull happened at, 60 centimeters, divided by the distance gravity happened at. This happens to be 20.16 newton. And of course, since the force of gravity is just mass times the acceleration due to gravity, we can divide by the acceleration due to gravity and find the mass of the beam. And I get 2.05 kilograms. So that completes the first activity. This is the mass we're going to use for the rest of this lab. Of course, we could use the force due to gravity, or we could use the torque due to gravity, which is this times that. But that information is going to be part of the rest of this lab because now we know the beam has some gravitational force on it, and so it has some torque, so we need to take that into account when we do our equilibrium calculations. So activity number 2, predict the force required at 100 centimeters from the point of rotation at an angle of 125 degrees to keep the beam in rotational equilibrium, and then confirm that. So our data is at 100 centimeters, and our phi p is 125 degrees. Let's draw a picture of this. So here's our beam, the force is pulling from the end, here's the pivot, and that angle is just there because that's how we define the angle that goes into the torque formula. It's the angle between the radius vector, which is here, and the torque vector, which is there. So that angle, which is the same as that angle. So the torque due to that force has to offset the torque due to the gravitational force. The torque due to gravitational force is the force due to gravity, 20.16 Newton, times the distance, 0.42 meters. And again, you can see that we're getting close to that 8.4 prediction we had at the beginning, but we're using some measurements, so this number should be better than we had when we predicted it. So here's our equilibrium expression. The torque due to this pull is going to be the unknown pull times 100 centimeters times sine of 125. Putting that into here using this for the gravitational force, and remember to convert into meters, we predict that it should take a force of 10.34 Newton at that angle to keep this beam in balance. So let's check to see if we're right. All right, so I've got my protractor at 100 centimeters. I'm using the red force sensor because my prediction is right in the range of the red force sensor. I'm going to hold this at 125 degrees, and I read that I get 10.5, maybe 11. So let's call that prediction that measured 10.75 because I couldn't really tell, but that's certainly a confirmation that this approach worked. 10.34 versus 10.75, that's very close. All right, so we've done the first one, we've done the second one, now let's do the third one. Same basic idea, but we're changing the position and changing the angle. So the theory here is exactly the same. Here's our equilibrium for torque. Here's rewriting it, putting in the relevant variables. With the angle at 35 and the distance of the pulling force at 40 centimeters, our prediction is 36.9 Newton. Okay, let's go set the beam up and see if we can verify that. Okay, so I'm back at my beam. I've picked out the yellow force sensor because the prediction is between 20 and 50. I'm trying to get 30 degrees, 35 degrees. Okay, reading out the force sensor, I get 33.5. Okay, so 33.5 Newton is what I measured. That's not real close to the predicted value. So if you recall, the criteria that I've been using in this class for when a measurement is accurate is something like a 10% leeway on either side of the value. So if you calculate the percent error on this measurement, you get 0.092, that's 9.2% error, and so I'll count that as accurate enough for what we're doing. The force sensors are not real accurate. It's hard to get the angle measurement right. If that protractor is not exactly level, that can have a pretty big impact. So I'll take this as a confirmation that I know how to use the torque formula to figure out what the force is that I need to balance against gravity. All right, so that takes care of our first three activities, and now we want to go on to the next one, which is repeating the previous one, but adding a mass of 200 grams to the end of the beam. So I'm going to start by writing the sum of all the torques. The additional mass is going to add an additional torque. So TP is what I'm pulling with. TG is the gravitational force from the beam, is acting on the beam by causing a torque. And this is the torque due to the extra mass. It is not at the same location as the center of mass of the beam. This is at the end. The center of mass is halfway down. And so they have to be in separate torques. They are separate points, so they exert separate torques on the beam. And of course that's equal to 0 because we are going for rotational equilibrium, no angular acceleration. Okay, so here's that equation rewritten. Distance force sine theta as before, gravitational torque on the beam, and 0.2 kilograms times 9.81, acceleration due to gravity times the distance times sine 90. I'm going to make this as close to 90 as possible. That's equal to 0, and so again, I can solve for what Fp is, given that I know what the angle is. My predicted value is 45.5 newtons, so let's check that and see if I get the right answer. Alright, so here's my beam setup. I've got the extra mass hanging off the end here, 200 grams. I've got the yellow force sensor, because I'm going to register a pretty large force, so I need to use the least sensitive sensor. 35 degrees, try to keep it in equilibrium. And it seems to be 44, right on the dot. So I measured 44 newtons. We can calculate what the percent error on that value is. I get 0.034, that is 3.4%. That's real close, so I think I've confirmed this example of using torque in rotational equilibrium. Alright, so that takes care of the fourth activity. So now for the last activity, we're going to calculate the force that the pivot point acts on the beam with, remove the pivot point, and see if we can get our force sensor to confirm what we calculate that force is. So I'm going to start with just a diagram. Here's my beam, there's my pivot point. And here are the forces I'm acting on the beam with. This is the gravitational force at the center of mass of the beam, the force of the mass at the end of the beam, which I added in part 4, and the force that I'm pulling with. Well, now I have to observe that the force that I'm pulling with, this upward force, is certainly not balancing out all of the gravitational force. And more importantly, there is a sideways force from a pulling force, which is not being balanced out by anything. So this pivot point needs to balance out the rest of those forces. So I'm going to explicitly split that force up into x and y components, Fy and Fx. And I've been using torque this entire time, but because now I'm going to consider the beam in equilibrium not just with respect to torque, but with respect to translational motion, because the reason that there's an Fx force here is to balance out this force, so to prevent the beam from accelerating in the sideways direction. I'm going to use Newton's second law in the translational sense, not in the rotational sense. Also notice that I've picked Fx and Fy to be in the standard x and y coordinate system directions. I should expect Fx to be negative, because it has to balance out this component of Fp. So actually Fx is in this direction, but I've set it up like this, so I should just expect Fx to be negative. So here's my sum of forces in the x direction. This is F that I pull with in the x direction, and this is Fx, which I anticipate here and I want to calculate. So I measured 44 newtons for the force of the pull, so that's what I'm going to put here. I'm not going to use my calculated value, I'm going to use my measured value because I believe that to be a more accurate value. Cosine theta, this theta is 35, so I want the adjacent side, and Fx is what I'm looking for. And at the end of that calculation, I get 36.0 newtons negative in the x direction, so this is going like that. So here's Newton's second law in the y direction. This is the pulling force in the y direction. This is what I'm looking for. And then I put negative signs in front of the two gravitational forces because they are pulling the beam downwards. So I can solve that equation so that Fy is the gravitational force on the beam. This I calculated earlier in this video. This is m times g of the mass at the end of the beam. And this is the y direction of the pulling force with a negative sign because that one is going to be decreasing how much force in the y direction the pivot point acts on the beam with. So I get negative 3.11 newton. So it turns out that this force is also acting in the negative direction. It's like there. So the beam is actually being acted on by the pivot point in the negative x and y direction, so it's going off in that direction. And I just got that as a result of setting all the forces equal to 0 using Newton's second law. That could have happened. It could have happened that the forces were acting in the positive direction or the negative direction. It just depends on the combination of the forces on the other side of the beam. We shouldn't necessarily assume that this pivot point is doing anything, acting in the positive direction, acting in the negative direction, doing anything else. Only Newton's second law can tell us really what that pivot point is doing. So in order to confirm that, I need to figure out what this angle is because I'm going to stick a protractor right there and try to figure out if I can set this balance up. So take the inverse tangent of Fy over Fx, I get 5 degrees, and so this angle is very, very shallow. In addition, I'm going to need the magnitude of this force, because what I'm going to read on the force sensor is actually the magnitude, not the components. And I get the magnitude using the Pythagorean theorem as 36.1 Newton. So that's the magnitude. Here is the direction. Now, the challenge is to go set this up on the beam to prove that this beam will be in equilibrium. Alright, so I'm here with Professor Craig Looney, and we're going to try to set up this beam balance. We've picked out the yellow force sensors because those are the ones that have the most appropriate range for what we're trying to measure. The way we're going to test this is we're going to set up the two forces and the angles, how we've calculated them to be, and then see if the beam is going to be in balance. So I'm at 35 degrees and 44 Newton. Craig has set his up at 36 degrees, 36 Newton, negative 5 degrees. Let's lift the bar off and see if it's balanced. Perfect. Dun, dun, dun. The prediction is confirmed, and we can say that we certainly understand how to calculate torques so that they are in rotational equilibrium. Alright, thanks guys. Thanks for watching the video. And I hope this helped you understand how torques work and how we can use them to predict things in the real life.